Okay, hello there. Let's get started. Okay, so today we're going to talk about intermolecular forces. These are the learning objectives that we will be working on. And as you know what the pencil on the screen means, and as well as if you see the phone. Okay, so let's define intermolecular forces first. Okay, so intermolecular forces are attractions between molecules. They keep things together. By things, I mean molecules or atoms, etc. And they determine the physical properties of a substance. Okay. So if I came to you and I was just like, okay, can you define intermolecular forces for me? Some things that you could probably say is how things are kept together. Okay. Another word is inter. Inter, it has the letter E in it. And I want you to remember the E's in between. This topic is going to come back time and time again where I ask you like, what do you like mean by inter between molecules or intra? We're gonna talk a little bit about ionic covalent bonding when we do our collaborative session together, and I'm gonna ask you to differentiate how intermolecular forces, which are between molecules, different than those intra, which is ionic and covalent, etc. Also, I found the TikTok video, so make sure to check it out. Okay, so why study about intermolecular forces? You guys remember that thing that happened like 5 years ago when we're all wearing masks and Purell was crazy, there was no toilet paper, etc. Yes, COVID-19. So one of the many applications for intermolecular forces happens during like for our immunity. So what exactly happened with this COVID-19 virus? So COVID-19 virus has these spike proteins, and they are actually attracted to your cell via these intermolecular forces. Now, what happens with the vaccine? The vaccine, an antibody will attach with those same intermolecular forces to your cell, blocking these spike proteins from the COVID-19 virus to attach. So intermolecular forces between molecules have varied application. I just wanted to talk about this for folks who want to go into medicine or pharmacology in the room. Okay, so let's first identify location of intermolecular forces. As I talked about, these are between molecules. So let's take a look at between two of the same molecules. You've got a hydrogen molecule on the left, hydrogen molecule on the right. Both of them are just chilling, having fun, and something happens. And then there is an instantaneous dipole. And if you remember from our previous uh, discussions about dipole, there is parts of the molecule that densely pack those negative charges and result in partial negative, and then the rest of the molecule will result in partial positive. Okay. Now, what happens if this molecule on the right starts, going towards this molecule on the left? And there's an instantaneous dipole, but this molecule on the right, chilling, there's no dipole there. It's a nonpolar molecule, as you remember. And then boom. As soon as it gets closer and closer, there is an induced dipole in our molecule on the right. What does this mean? It means because of the charge separation that occurred on that left hydrogen molecule, now when that right hydrogen molecule came closer to it, it also established a temporary or instantaneous dipole. And because of this, as we know in chemistry, opposite charges attract. Therefore, the partial negative charge of one is going to attract the partial positive charge of the other. This is intermolecular forces. Okay. And if it's all not making sense, that's totally fine. When we work on the collaborative activity together, you're going to get this, I promise. Okay, now let's take the water molecule, right? The representation that you're seeing on your screen is an electrostatic potential map, as you might have seen when we talked about polarity. So if you remember, the redder the region, the more negative, densely negative charge, and the bluer the region, the more densely positive charge, right? So again, my water molecule is chilling. What happens if another water molecule that already has a dipole? So there's dipoles in like both of these guys, right? Boom. It's going to reorient itself in order to stay attracted to those partial positive, partial negative, et cetera, et cetera. Okay? Intermolecular forces are between molecules. They will also occur between different molecules. Here I've got a CO2. It is non-polar. Everything is where it needs to be, and then it come closer to this water molecule, and then boom, it has to reorient itself, as we can see. Okay, so intermolecular forces between inter, right? It's between. It's not within, it's between. And during that collaborative activity that I talked about, we'll talk more about this, okay? Okay, let's do some clear questions. So talk to your neighbor, talk to the person in front, talk to the person at the back, and let's solve this together. I'm going to give you a little bit of time. Which of the following is chemically correct statement? And make sure to also chat with your learning assistant. Okay, let's come back and let's take each statement on its own merit, okay? Intermolecular forces keep sodium and chlorine together in NaCl. Well, we know that intermolecular forces are between molecules, right? Sodium or chlorine, they actually form ions. So therefore, this is ionic bonding, as you may recall. Okay, if it's not clear again, more practice is coming. Okay, intermolecular forces keep electrons attracted to the nucleus. Yes, intermolecular forces are between those partial positives and partial negatives. However, they are between molecules, again, not between electrons and nucleus. If you remember from our earlier chapter, this is a different type of force. Okay, intermolecular forces keep acetic acid molecules together in vinegar. That's a candidate, right? Acetic acid molecules are molecules. They have their own partial positive, partial charges in between them. Vinegar, a household staple. So this could be our possible candidate, okay? Let's look at option D. So intermolecular forces repel molecules away from each other. So we did talk about how the molecule needs to like reorient itself so that the partial negatives and partial positives are attracted to each other. So it's not completely correct statement because intermolecular forces tend to keep molecules together, but with the reorientation that the molecule has to do, obviously the partial charges that are the same, they will repel each other. So it's not entirely correct. So we're going to go with C. Okay. So again, take some time, talk to your neighbor, talk to your learning assistant, and let's discuss. Okay, let's come back. So lactic acid and salicylic acid are the two molecules that, or substances that are actually quite common in your skincare routine. So today when you go, do some skincare, you can think about this question. Okay, so let's look at the region. Here again, you're seeing electrostatic potential maps. The redder the region, the more negative charge. The bluer the region, the more positive charge. And then where's the location? So if we take each option, you have region 2 here, that's the blue, and region 4 here, that's a good candidate, right? Region 1 is here, region 6 is here, and green, so not blue, not really red. So, we can't really like judge at this point, right? Region 5 is blue, which means partial positive, and region 2 is also blue, which also means partial. So a good candidate for us. Okay, so in next class, we're going to talk about the next, which are these different types of intermolecular forces, and this is the really fun part. So thank you, and I will see you.